So in the previous video, we saw how a single leader replication system works and how the leader is taking in all the heavy load of taking in the write requests. In order to overcome that, we can add multiple leaders. But will that create any new problems? Let's find out. Welcome back, engineers. In this video, let's look at multi-leader replication systems. So when we discuss single leader systems, we saw that there is only one leader and the leader is responsible for taking all the writes and propagating the updates to the followers, right? And because the leader is taking in all the writes, there is a compromise on the write throughput. We have good read throughput because we have some kind of load balancing with followers, but the write throughput is compromised. To overcome that, we can use multi-leader systems. So let's see multi-leader systems now. So a multi-leader setup would look something like this. So we have a data center 1 where there's a leader and it has multiple followers, and there's a data center 2 located at some other physical location, and this is also having a leader follower concept, right? So the followers can be in different data centers themselves, but just for simplicity, I'm keeping all of them in one data center, right? So how this works is the web servers can talk to either of the leaders, and all leaders can take in writes, and they have their own database. They keep their current state, and once they have any update, they will propagate the request to other leaders. So there can be one leader, two leader, there can be multiple such leaders, and everybody is talking to each other through some mechanism and keeping everybody up to date, right? So whatever change is happening in any of the leader are propagating towards other leaders, and somehow everybody is kept in sync, right? So what is the benefit of this? We can achieve more write throughput, first thing, and we can also position the database leaders across the globe so that I can talk to my nearest leader, right? That way we are achieving some performance improvement too. So what is the trade-off in this? So in multi-leader replication system, once a leader receives any update or insert or any delete command, it needs to propagate over the network to database leader, and this has to happen asynchronously, right? Even though they're communicating, it is not a synchronous sync, it is asynchronous, because this leader needs to keep on receiving new writes and it's not stuck because the other leaders are yet to update, right? So that would compromise the whole system. In single leader replication system, we saw that the leader could have some kind of consistency with the follower through semi-synchronous mechanism, but that is not possible with multi-leader systems. So all data communication between leaders is asynchronous, and because of this we are going to achieve eventual consistency and not a strong consistency. So that is a trade-off there. So we are getting good speed and performance with multi-leader systems because we are able to reach our nearest leader for our writes, but the compromise is that there is eventual consistency. Now let's see where we might use this. So for some apps where we might need offline support, this is especially useful. For example, this OneNote editor, I'm able to use this online or offline. And when I'm making changes offline, it is not stopping me. It is allowing me to make those changes. And when I'm back connected to the internet, it is syncing with the server, right? And there are also apps where collaborative editing is required. So like Google Docs or code editing files, right? So in these apps, multiple people are working on the same document, and they all can be working connected to the internet from different locations, and everybody can work together, and they can reach out to their nearest leaders and continue their updates, right? So when you think about it, every device in itself is a leader, right? Because even when I'm offline, the system is accepting my writes, which means my own system is a database leader. It is accepting writes and it is propagating those writes to other leaders, let's say some servers across the globe, right? So in these kind of situations, we can use multi-leader replication because we are okay with eventual consistency. Even if the sync is delayed by a few seconds, I'm okay with that. These are not so critical in nature when compared to other banking systems or any financial transactions which require very strong consistency, right? So these are some use cases of multi-leader systems. Now let's compare this with single leader replication. Let's see what happens in terms of performance. So in single leader system, there is only one leader who's taking in the writes. So this leader has to be present in one physical location, right? And all users from around the globe are talking to the system. So let's say the server is in India, but I am having users across the globe from London, US, or maybe Australia. And the distance between the locations are quite different. So the number of network hops that the request needs to make to eventually reach the leader is actually quite different when it comes to different locations. So that is a compromise on single leader, but we eventually reach there, and that's a strong consistency. But in the case of multi-leader systems, we have a benefit of placing the leaders across different locations, and I can talk to my nearest leader. So that way I'm getting better performance when compared to single leader systems, because the request needs to travel a lot less, right? So that's about performance. Now let's talk about data center outage tolerance. So in the single leader system, let's say the leader and followers are in one data center. So if the data center itself goes down, everything is stopped, everything is crippled. So in order to avoid that, we can keep the followers in different data centers outside from the main leader, right? That way, when the leader data center goes down, the follower data center can take its place, right? But in the meanwhile, the writes are a little delayed. So that's how the failover works in terms of data center. But in multi-leader system, we have a better tolerance, because even if one data center completely goes down, the writes can continue to happen to other data centers. So the users are not blocked and our writes are not compromised, right? It's just that the data center one, when it comes back up, it needs to catch up using asynchronous sync, but that's okay because our writes are not compromised. So that is one fundamental difference when it comes to data center outage. Now let's talk about network tolerance. So in the single leader system, if database followers are in different data centers, like we discussed before, the leader needs to propagate the changes to the followers. And because it needs some kind of strong consistency, the leader is actually waiting before at least one of the follower or majority of followers have reached and concluded that they have received the updates and they have updated themselves, right? So there is a strong coupling between this. And because they are located in different physical locations, there could be multiple network problems that can arise. There could be delays, there could be network interruptions, and all of these are adding to the complexity of this single leader replication system. But in the case of multi-leader replication system, because everything is asynchronous, we are not having a lot of network issues. At least we are not aware of these network issues. So even if when there is a delay between one data center to the other, it's still okay. And eventually they will catch up and somehow they will all be in sync, which is what we need, right? So that is a fundamental difference in terms of network tolerance. So there is no right or wrong. They both have their use cases, and we just need to keep in mind about all these when doing a system design for different types of use cases, right? So that is a fundamental comparison between single leader and multi-leader systems. Now let's see some replication topologies. So we have three such examples. First is a circular topology. So in circular topology, whenever a write is coming to a leader, the leader forwards a request to just one more leader, and that leader forwards to next leader, and so on, right? So in this way, all leaders are kept in sync. So this is one of the topologies. So in the second topology, which is the star topology, one of the leaders is designated to do this job. So every leader, when they receive a write, they send it to just one node, and this node is responsible for propagating the request to other nodes. So this is one of the other topologies. And the third one is all-to-all topology, where everybody is talking to everybody else and every update is being sent to everybody else, right? So these are three different kinds of topology. Now let's see if there are any challenges to these topologies. So in circular and star topologies, for one update to be completely synced across all the leaders, it needs to travel through multiple nodes, right? And here as well, it needs to travel through multiple nodes before it is completely in sync with all the leaders. But in all topology, because everybody is talking to everybody else, there is direct connection with all the leaders and there is no hopping in between. So the updates are going directly to all the leaders. Now with all-to-all topology, this might be looking like a great solution, but it has its own challenges, especially when it comes to causal dependencies, right? For example, some nodes might be closer to each other than the others, and the updates might travel faster to these nodes than the other nodes because there is some kind of network delay or there's a long distance between them or anything like that. And some updates might go in faster to some nodes than the other nodes. So let's say this update has reached node 2 and somebody is reading from here, they will receive a faster update than users reading from this one. So again, that is something to keep in mind when dealing with multi-leader system. So once again, we are seeing the compromise between speed and eventual consistency in these cases. So those are some of the topologies in which the leader systems can be connected with each other. Now let's see how they actually talk to each other. So they use a concept called gossip protocol. So with gossip protocol, each node is communicating to the other node periodically to check if the other node is active and healthy, and they are communicating with each other for the updates. There is no intermediary between these nodes who's doing the coordination job. The nodes themselves are talking to each other using gossip protocol. So this is different from WebSockets, because in WebSockets there is a continuous bidirectional communication, but this is more like a peer-to-peer communication network, and it is not a persistent connection between these nodes. So there are connections being established to check for updates and health checks, and that's how they're all kept in sync. Now the biggest downside with multi-leader replication systems are write conflicts. So in the next video, we will see what are write conflicts, how to detect write conflicts, and what are some of the strategies to actually solve this. So it is a very hard problem to solve. There are multiple use cases and edge cases. We will try to touch upon them on a superficial level, and then we'll try to go deeper as required. So I hope that you got some introduction to multi-leader replication systems in this video. I will quickly see you in the next video, guys. Thank you so much for watching. Do leave a like if you found this helpful. Do subscribe so that you don't miss out on the future videos. Thank you so much for watching. Cheers.